Background, when we talk about erosion and sediment control here in the country, we have an estimate of 80 million tons of sediment that gets washed into our waterways each year. And this is just from construction sites. To put that into perspective, it's a huge number. 80 million tons would fill enough dump trucks to fill 9 lanes of highway between LA and New York. So try to picture that. It's a huge amount of soil, and obviously it has a huge impact on our natural ecosystems. So in order to mitigate the issues related to erosion and sediment loss, we employ several different types of practices, best management practices on construction sites to try to keep that soil in place and try to catch it before it leaves the site. So today I'll talk about a series of different practices we investigated doing our research studies, but these are just kind of a sampling of typical practices you would see on a construction site. You have practices that go along channels, practices such as sediment basins that are designed to detain stormwater, inlet protection, you've got your perimeter controls, and they all kind of have different ideas or different ways of performing. However, even with these practices, these best management practices employed, we still have sediment-laden discharge that comes off of our sites. And you can imagine what kind of impact that has on the natural ecosystem in that waterway. In Alabama, our rivers literally turn orange after a rain event. So imagine anything trying to survive in that water after significant runoff. And so we have there's a need to improve the controls that are used, the temporary practices that are used on construction sites. At Auburn, we've got a really neat testing facility that we developed over the years. It's housed at the National Center for Asphalt Technology, NCAT. And NCAT is kind of a unique world-class facility. It's a 1.8-mile oval test track, and what they do is accelerated pavement performance testing. So they've got the test track broken up into different sections, and they run super weighted tractor trailers in circles for 18 hours a day. At that facility, we've got about 2 acres dedicated to stormwater testing. We call it the Auburn University Erosion and Sediment Control Test Facility. And the test facility was developed in collaboration with the DOT as they were trying to improve the practices that they use on their construction sites. The way the facility works is that we have this parking area up here for the asphalt test facility, and that collects stormwater and drains into this upper storage pond. We use that pond to pump flow into our different test apparatus, and that all gets treated in the sediment basin before being detained in our lower detention basin. So over the years, we've developed several different research apparatuses at the facility, looking at sediment barriers, looking at erosion control blankets. We've got channel testing, sediment basin testing, skimmer testing. And then in addition to all of those testing apparatus, we also have demonstration areas that we can use for training. So every year we host live training events out at the facility to get contractors, developers, inspectors all up to speed on how to properly manage stormwater on construction sites. So our 3 main areas is research. We also have product evaluation for products that are trying to get on the DOT's qualified product list. And then we also do the training, our hands-on training. So the first project I'm going to talk to you about is one that I worked on during my master's, and we were looking at inlet protection practices and how to improve them to retain sediment around storm drain inlets. So to kind of give you a little bit of background, inlet protection practices are required for all inlets that are not routed through a sediment basin. The idea with inlet protection is that you are impounding stormwater around the outside of the inlet and allowing soil particles to fall out through gravity. Typically, the drainage area for these inlet protection practices is limited to 1 acre, so you shouldn't use them if you have more than 1 acre draining into the barrier. So these are some of the common practices we looked at: silt fence, sandbags, wattles, straw-filled wattles, aggregate barriers, and we also looked at some manufactured products that have kind of become popular in the industry. These practices and products, they have a lot of different failure mechanisms. A lot of them have to do with the way they were installed. But we deal with things such as short-circuiting, bypass around the practice if it's not properly installed. Undermining is very common. Structural failure, and that's also due to poor maintenance and poor installation. And then improper installation, where this practice wasn't even trenched in. It just becomes a erosion control theater, I like to call it. In all of our testing, what we're trying to do is replicate field-like conditions. So we do a hydrologic analysis, we do a soil analysis, we look at our curve numbers, we conduct a TR55 analysis, looked at our universal soil loss, and we really come up with a testing regime that mimics what these practices would be subjected to out in the real world. So for this particular test, we were testing at 1.25 cubic feet per second for a duration of 30 minutes, and then we're introducing soil as well. So we installed a test channel to mimic a highway median. So it's 40 feet long, 20 feet wide. We've got a section that's plated in steel just to allow our flow to kind of equalize and to minimize the erosion in that area. But then on the bottom half of the installation, we've got just a bare earthen soil area where we can install a practice the same way it'd be installed out in the field. We introduce flow into the system using a regulated system that we've come up with where we can control the amount of flow coming in to the test apparatus, and then we auger in soil and we meter it in at the rate that would be expected, the soil loss would be expected on the site. We collected as much data as we could during these tests. We're looking at flow rates, we're looking at water quality, taking grab samples upstream and downstream. We conducted surveys of the entire test apparatus before a test and after a test so that we can account for how much sediment was collected and deposited upstream of the system. And you kind of see the surveying here using a robotic total station. And then we start improving practices. So the way we kind of went about this was that we would take the DOT's standard installation, we would test it to see how well it did, and then we would try to provide improvements if there was improvements that could be made. So this first installation here, this is a straw wattle barrier. It's constructed in a ring around the inlet, and you can kind of see the standard DOT details here. But basically use a 20-inch wattle. It's installed around and overlapped about 12 inches. And then we use TP staking to hold it down and secure it in place. So this is a time-lapse video during testing. And a couple things to point out here is that these practices are intended to impound water outside of the practice or outside of the barrier. And you can see there's very little impoundment occurring here. And you actually see a lot of that water flowing underneath the practice. And if you look closely, you can actually see that water is buoyant. So the majority of the water is not flowing through, it's not flowing over, it's flowing underneath. So it's completely wasteful to have this out there. You might as well not have anything, to be honest. And you can see from the post-test picture, you got a lot of deposition inside of the barrier and a lot of erosion within the channel leading up to the practice. So we looked at ways of trying to improve this, and we went through several different iterations, and this is the one that ended up working out the best for us. So basically what we did was we reduced the diameter of that wattle barrier. We added a geotextile underlay. That underlay was to help reduce the amount of erosion and scour occurring under the practice. So we reduced the diameter. We increased our wattle connections. So we were seeing a lot of short circuiting where water was flowing in between the wattles. So we increased the length of those to 18 inches. And then we also modified our staking pattern where we're still using the TP staking style. We call it a non-destructive method. We're not piercing the product. But then we also add these staples. Add the staples on both the inside and outside of the barrier every 10 inches. And what we saw was that with the staples, we were able to impound a lot more water outside of the practice and actually get it to overtop. And you can see here, that's kind of our schematic that we came up with. We've got that 8-ounce geotextile underneath, and it's pinned all the way around. And then the installation is staked and stapled down. And here it is during testing. You can see you still have some flow going underneath the practice, but at least we've got that geotextile to where we're not losing soil underneath and making the system perform worse. At the low spot, we've got overtopping, so it's impounding to the full height and full storage availability of the practice. And you can see that we're now protecting our channel from those high flows that were causing the erosion. And you can see here after a test now, our channel hasn't eroded. We've got some deposition around the practice. One thing I did want to point out is that you don't see much flow actually going through the wattle. So don't think of these systems as filters. What they are is they create an impoundment, and that's where you get your treatment. It's those particles falling out of suspension by that reduced flow, reduced velocity. The next, we looked at silt fence barriers. So we installed it using the typical ALDOT installation method, a 6x6 inch trench. They use a wire-backed type silt fence. It's non-woven. And then we tested it out, and 2 minutes into our 30-minute test, this is what we get, which is actually pretty typical if you walk around construction sites and look at some of these barriers after a storm event. This is what ends up happening. So we figured, okay, this is an easy fix. We'll just add more posts, right? So we added 4 more posts to the system, and 5 minutes in, we get total failure. So we came up with a way where we had to actually stabilize and reinforce those posts a little better. We ended up doing that with 2x4s. So this is after a series of maybe 5 or 6 different tests where we tried different materials, different post types, different configurations, and this is what ended up working out the best. You can see here we're still using the steel T-post. We've included an underlay to reduce the amount of scour underneath. And then we've got this unique dewatering board here, which I'll show you a little bit more in a minute. So something neat about this installation with this cross bracing with this underlay is that now we can't trench in our silt fence. So instead of trenching it in, we pinned it. And here's a close-up on that. But every 5 inches, we put a sod pin. They're 6 inches deep. They're real easy to drive into the ground. And actually, the installation was a lot easier than creating that trench and burying our fabric underneath. And then here's our dewatering board. So this practice performed so well that we had impoundment around the barrier for more than 24 hours. So we had to come up with a way of safely discharging in a controlled manner some of that water that was impounded. You can see here during our time lapse, you don't see any deflection on the structure. It's, from a structural standpoint, it performs very well. And then we're able to dewater that entire impounded area within 24 hours using that dewatering board in the back. Here's kind of a close-up looking at the dewatering board. And here it is after a series of tests. You can see a significant amount of sediment has dropped out back here. And one of the neat things that we saw with this practice was that you create such a large impoundment that sediment starts to settle out way upstream of the practice to where you're not having a whole lot of maintenance right at the edge of the barrier. So it makes it easier from a maintenance standpoint. We looked at aggregate barriers. So this is a modified block and gravel system we came up with. We've got cinder blocks laid in a square pattern on top of a geotextile, and then we have a geotextile that's actually wrapped around the blocks as well, backfilled with number 57 stone. And then we have a dewatering mechanism in the back where we've overturned one of the blocks, cut out a quarter of the opening on the geotextile, and we've got a wire mesh there as well just to keep rock from washing in. And that performed very well as well. You get full impoundment, you get overtopping. Those are kind of the conditions that you want with these inlet protection practices. And then you can see the deposition that occurs. Again, way outside of the barrier. It's where that hydrostat or that jump occurs on your flow. And you can see that there's very little clogging of that aggregate because you're dropping those heavy sediments, those rapidly settable sediments, out upstream of the practice. We also got creative, and we wanted to see what else we could come up with that might be more innovative or might perform better. So this is a GABION flow system. We tested out basically 2 rows or 2 configurations of the silt fence, and we've cut in weirs to route flow through the practice. You can kind of see it working here. The water comes in through the front or through the back, and it's routed through the system and then deposited inside of the basin. And this time-lapse kind of shows you as we turned on our sediment introduction, you can see that plume of sediment flowing through. The idea with this is that if you were to dose with flocculants, this would be a good way of doing it because you get good agitation with the aggregate and the riprap that's been placed inside of the barrier. So to kind of summarize some of the costs associated with the practices, we were interested not only in how well it performed from an installation standpoint, but also the cost to the DOT. From that standpoint, silt fence and sandbags were one of the cheaper options. I didn't show sandbags because it wasn't very exciting. But then we also were able to get very good impoundment with that silt fence, and that's just a function of the height of the barrier. And that correlated to more sediment being captured around the system. We looked at water quality, and interestingly, water quality was not improved by any of these practices. So it did a very good job of capturing total solids and capturing the heavy sediment particles that fell out. But from a turbidity and total suspended solid standpoint, we got no improvement. So you actually see that upstream of the practice, you have lower turbidity than downstream. And that's just because we have that earthen channel that contributes to additional sediment leaving the system. We did see a decrease in turbidity after time if you detain that storm water. So after the storm is over, and you continue to impound that water and slowly release it, that's where you get the improvement in turbidity. So some of the highlights or some of the key takeaways from this project were that adequate staking and bracing is required to get a well-performing practice. You need to have an overflow mechanism if you expect to have flows that are going to exceed the capacity of the barrier. You can do that using spillways or weirs. Prevent undercutting, so the geotextiles came in very handy to help out with the scour issues we were seeing. And then having some kind of dewatering mechanism so that we don't create a flood hazard around roadways and areas prone to flooding. So next I'll talk about a project where we looked at ditch checks. And ditch checks or check dams are used in channels to slow the velocity of water. And pop quiz, are they an erosion control or sediment control? Any takers? They're actually an erosion control. The primary benefit with using ditch checks is that you slow the velocities down in the channel and you reduce the scour and erosion potential of that flow. As a secondary benefit, you're slowing down water so you get some heavy sediments to settle out. They should be considered an erosion control before they're really considered a sediment control. So our test channel is very similar to the inlet protection channel. It's about 40 feet long. We've got about 20 feet in width. And again, it just mimics a roadside channel. We looked at straw wattles, and this was the old Alabama DOT installation where they would actually pierce through the wattle. And then we would provide improvements to that as well. You can kind of see the impoundment that system creates. So very minimal impoundment. The reason for that is because you're getting a lot of undercutting, a lot of scour underneath the wattle as flows coming through. So we looked at ways of improving it, and sometimes our improvements created such a large impoundment that we would get failure of the system. So there was a trade-off between how much you can actually impound upstream of the practice and how much the practice would be willing to take. So these were always fun days out at the lab where you get catastrophic failure. So some of the recommendations we came up with for using wattles as a ditch check were to again include a geotextile. That's a very common theme to help reduce that scour. This is actually trenched in along the front end and then pinned down on the back end. And you'll see again with this staking treatment here, we're not piercing the wattle and we're providing bracing so that when water's pushing the wattle behind, it's actually digging it deeper into the ground. One thing I do want to point out is that a lot of these practices or products are sold as filters. And you can see here from this picture, there's not a whole lot of filtering going on. And the water quality tests that we do always kind of show us the same result, where water quality is not improved after passing through the system. We do capture sediments upstream, but that's a function of the impoundment created, not of any kind of filtering or turbidity being treated through the system. We looked at riprap as a ditch check. This was the standard DOT installation. Get an impoundment of about 15 feet. We looked at adding choker to try to decrease the pore passage between the aggregate. That increased our impoundment by 20 feet. And the last treatment we tested was using a geotextile fabric wrapped around the barrier. You can see it's pinned down in the front and just wrapped around the aggregate. And that, well, I didn't show, that impounded all the way up to the mouth of our setup, 30 feet. So just by making those minor changes, going from a system where you don't have any aggregate to adding some kind of blockage to reduce the flow through the system, you can significantly increase the performance of the practice. And if you can go from, we almost doubled the performance of aggregate, going from 15 feet of impoundment up to the 30, the full edge, the full size of our test setup. You can basically, you're doubling the performance of that practice. So, and that's a relatively easy modification to do out in the field. You add 10, 15 feet of a geotextile, staple it in, and kind of leave it there. And the beauty behind this is that once that fabric kind of blinds, it's very easy just to take it off, remove some of the sediment that's accumulated, either place it back on or replace it with a new fabric. So it makes it very easy from an installation or from a maintenance standpoint. Sandbags is another practice commonly used by the DOT. They use these in areas where they've already maybe permanently stabilized with a concrete flume or concrete channel. Their standard setup didn't hold up very well. You can see here during one of our higher flow events, the bags become dislodged and you have catastrophic failure. So we looked at ways of reinforcing that installation. Basically, the easiest system we could come up with was to just rotate that center bag to the center line. So instead of all bags running parallel, that middle row is now perpendicular to the bottom and top. And that helps lock in the bags much better. And we also have a spillway system set up so you can dissipate the energy of that flow as it falls over top of the practice. Oh, there's my, it was out of order. So that's the wrapped aggregate riprap ditch check. So 30 feet of impoundment, 29 feet of impoundment. One of my favorites was this silt fence installation that we came up with. So silt fence actually performed very well from a ditch check standpoint when it was installed correctly. But the issue was that you were having to run your silt fence outside of the test channel or outside of your area to contain all that impoundment and prevent water from flowing around the silt fence ditch check. So we came up with a way where we can minimize the installation needs or the materials being used in the installation. And that was by cutting in this weir system into the ditch check. So what that weir allows you to do is to direct flow over the center of the ditch check and prevent any kind of runoff from going around the edges. And you can see here again we've done the pinned installation where we have an underlay, and then the silt fence on the front side is not trenched in but it's pinned in. You can kind of see the pinning system here. So it's an underlay with then the silt fence fabric pinned on top. And you can see that during testing you get that flow to go through the center. We've cut the weir here so that it's no higher than this point, the highest point on the practice, so you don't get flow short-circuiting and going around the practice. We also wanted to see how this would perform from a longevity standpoint. So we ran several tests over a series of months. We did about 6 or 7 tests. And you can see the deposition upstream of the practice. So this is providing no maintenance in between our test runs. And you can see from our survey, we got about 92% or 91% capture upstream of the practice. We did have some scour on the back end as flow starts to go through the practice and pick up some additional sediment. The DOT has employed a lot of these practices as their new standard. So this is what the ditch checks look like now on active DOT construction sites. You can see some of these are installed, hundreds of them are installed along their roadway improvement projects. So far they've been performing pretty decently. So with the ditch checks, underlay and staples increase performance. Choking port passages double the performance of that aggregate ditch check. The sandbags were able to sustain the higher flow rates just by changing the orientation of the bags and adding the spillway. And then the silt fence pin installation seems to be a pretty plausible option that's actually working. One of the newer tests that we've been doing out at the facility, or we were starting as I was leaving, was looking at sediment barrier practices. So these are practices that are installed around the perimeter of a construction site. Typically we think of it as silt fence, but it can include wattles, it can include three-dimensional flow systems, it can be aggregate. There's many different ways around it. With these practices, we see a lot of the same common failure modes. Fabric is unearthed. We have discharge that's kind of unregulated. It's going through failure points on the fence. It could be sediment bypass around an installation. Impoundments that just overwhelm the installed practice. Undermining, overtopping. Those are some of the common failures which I'm sure you've never seen before. The test apparatus we developed, we wanted it to mimic, again, construction site layout. So we went with a system that's 20 feet wide. This is an aerial view of it. That allowed us to install the practice here in this earthen section, kind of the same way it would be installed out in the field. So we've got a tank to introduce flow. We've got a sediment hopper to introduce our sediment to meter it in. And then that flow and sediment gets mixed in and introduced through this sheet metal area where it's dispersed evenly across the width of the installation. And then you see our installed practice down at the bottom that's subjected to these sheet flow conditions. And then we have access doors down at the bottom that allow us to remove and install something longer. So if we wanted to look in, let's say, a sliced installation method, we can easily do that, where we can remove the doors and have a tractor come through and slice in the silt fence like it would be done out on the site. And then recently we've added a pole barn to keep normal or natural rainfall events from messing up our experimental tests. So we went through a series of different tests out at the facility. We looked at different products and practices, and I'll just show some of the highlights in some of those tests. So the first system we looked at was the standard DOT silt fence. And the standard fence uses 10-foot spacing between steel T-posts. It's got a wired back reinforcing, and it's got a non-woven silt fence trenched in 6 inches by 6 inches. So with that, we saw a lot of deflection on the posts. We saw overtopping, no improvement on water quality, and sediment retention an average of about 82%. We looked at a sliced installation, so same fabric, same backing, except it's installed in a sliced with a tractor implement rather than with a typical trenching. So here you can see we've removed the doors on the sides, and we've installed this in kind of a smile configuration where water's going to impound down at the bottom. With that installation, we saw excessive undermining, which we weren't expecting. We actually thought the slicing would work better, at least that's how it's marketed, because we have less disturbance with that without a trench. Sediment retention about 66%, and then no improvement on water quality. We also wanted to see what our neighbors were doing. So Georgia doesn't use a non-woven, they use a woven silt fence. So we tested their silt fence. They use wooden posts instead of steel posts. That actually performed pretty well. It did have some minor undercutting, but the sediment retention was a lot higher, 90%. Again, but no improvements in water quality. So water quality is still an issue. Good question? So I didn't quite catch it. Something about this. So it's not just the posts that are different in between the Georgia and the Alabama installation. With the Georgia installation, it's a woven fence. It's a woven fabric. And then you also have spacing between the posts that's a lot closer. So with the Georgia post spacing, it's about 4 foot. Alabama DOT standard is 10 foot. So that's structurally, it makes a big difference from that standpoint. But other than the fence and the posts, it's installed exactly the same way with the trench, 6 by 6 inch trench. We looked at a sediment retention barrier. That's another standard practice in Alabama. Basically, it's 2 rows of silt fence filled with straw mulch in between. That did all right from a sediment capture standpoint, sediment retention standpoint at 90%. We still had a lot of post issues where it was failing from a structural standpoint. We looked at a barrier, sediment retention barrier with a flocculant. So here it's no fence, no silt fence. It's just straw mulch laid out with flocculant sprinkled on top. It's granular flocculant. No impoundment, obviously there's no fabric there to hold that water back. We do get some sediment retention upstream just by slowing down the water with that straw mulch. And our turbidity reduction, that's where we start seeing some improvements. It's when you're adding flocculant into the system. So about a 70% reduction in turbidity. And then we've also looked at straw wattles. So using straw wattles as a sediment barrier. With the straw wattles, significant undermining, very poor performing sediment retention compared to the other practices, 82%, and then no improvements in water quality. So I want to focus on how we took that sediment barrier, that ALDOT sediment barrier, kind of to the next level by improving the installation. And again, with these tests, we go through a series of iterations, but we always start out with the DOT standard install, and you see it here. So it's a 32-inch fence, 10-foot spacing on steel T-posts, and then a 6 by 6 inch trench along the bottom. And to keep that fence suspended, there's C-clamps or C-rings that are installed along the top on 2-foot spacings. So we do a series of tests. We run 3 tests to kind of simulate a longevity performance. And this is the third test. You can see you already have some sediment that's caked on from the previous test. But you can see how flow here just overwhelmed the fence completely, and that fence ends up overtopping. And that mass release of sediment-laden stormwater creates a big issue downstream. So we went through several iterations, and we wanted to see what can we do to improve the way these installations perform. We looked at several different treatments. First thing we looked at was the T-post. So there's different T-post options available. Commonly in the industry, we have what are called 0.95 pound per foot per linear foot densities, and we've got 1.25, 1.25 pound per foot posts. So we wanted to see if that made a difference. We tested different iterations using the two posts. We wanted to see if we reduced the T-post spacing, if we maybe added an additional post at 5-foot increments instead of 10-foot. What kind of improvement would that provide? We looked at reducing the fence height, so maybe we don't need to impound all 32 inches. Maybe we can reduce it down to 24 inches. And then lastly, we also looked at changing the way we were trenching in our silt fence. So with all of those installations or all those different treatments tested, this is the one that ended up outperforming all of them. So here we've offset the trench, and what we mean by the offset trench is that instead of trenching in right where the T-posts are at, we're actually moving that trench upstream 6 inches. So now we're not disturbing that area where the T-post was installed, and that's being installed in native ground rather than at the side of the trench. So then the fabric and the wire mesh is installed. And you can see now you can use a piece of equipment to roll up and down and get that trench compacted a lot better than you would be able to if it was right at the base of the silt fence, because you would damage the fence otherwise. And you can see the T-post. Now you've got an additional T-post. So we've got 4 posts for this particular installation. And you can see how nice and clean that installation is, because you're able to actually work around the practice without disturbing that area where the trench is at. So this is the third test, so the same test you saw with the failed practice. This is the third one. You can already see some of the previous silt that was on the fence from the last runs. And you can see with this, there's almost no deflection on the post. That fabric holds up very well. You got some minor undercutting at the areas of the post, so that's actually flow going through and falling out the bottom. There is some minor undercutting, but nothing compared to the previous test. So from a structural standpoint, this worked out a lot better, and our post deflection was 0.18. It's almost unnoticeable compared to the previous test where you had that catastrophic failure. From a sediment capture standpoint, 93%. So overall, this is what we've recommended to the DOT for them to implement as their standard installation. And then lastly, I was going to talk about my PhD work, which is looking at sediment basins, which are very common in Alabama, and some of the innovative testing that we did to kind of improve the performance of those practices. So sediment basins, these are temporary practices installed on construction sites. The idea is you're funneling all the storm water to these basins and allowing that water to sit there for a significant amount of time, usually 48 to 72 hours, allowing the soil particles to fall out of suspension. So the idea is that if you've used all your erosion and sediment control practices correctly upstream, your sediment basins act to just polish the storm water and treat that turbidity and treat that TSS that we're worried about. So the standard setup for a sediment basin in Alabama is that it's broken up into 4 bays using quarter baffles. And what those baffles do is as water comes into the system, it slows down the water, reduces the amount of turbulence, and allows you to use the entire effective width of the basin. And then at the back end of the basin, we've got a surface skimmer. So that skimmer is floating at the surface of the water, discharging from the top of the water column, which should be the cleanest, should be the most treated, as your heavier particles have fallen out to the bottom. And then we've got up in the channel leading into the basin, we've got a 4-bay, and we've got a flocculant introduction, which is optional on DOT projects. But if flocculant was to be used, it would be introduced up in this area where there's still time for it to be agitated before it comes into the basin and it's still in the basin. And another feature is we've got this spillway down at the bottom where excessive volume can safely pass through without creating an issue in the sediment basin. So in our testing objective, we wanted to look at a couple different treatments. We were interested in how those coir baffles were performing. We wanted to see if we can improve those. We wanted to see if we can improve the forebay upstream with the idea that we could capture larger particles and kind of limit the use of the basin for more of a polishing standpoint rather than a sediment capture standpoint. And we also wanted to treat or test this lamella settler idea, which a lamella settler is used in wastewater treatment. We wanted to see if we could apply it for stormwater treatment as well. I guess the whole idea at the end was to improve the current performance and provide the DOT with an enhanced sediment basin design. So like our other practices, we devised a mechanism where we can introduce flow and sediment at a controlled rate. Here we're mimicking the volume from a 2-year, 24-hour storm, and we're condensing it to 30 minutes so that we can get high flow rates and fill that basin in a very short time period. So we have a channel that leads up to our basin where we can test out our forebay setup before getting into the sediment basin itself. When it came to collecting data, we really instrumented the sediment basin with as many things as we could. The idea was to learn as much as possible as far as turbulence was concerned in the basin. Water quality, we had grab samplers that allowed us to take samples that we can take back to the lab and look at. We had level loggers that gave us an idea of the filling and storage of the basin. And then we also had data loggers with turbidity readings, so we could take turbidity at the different bays and see how treatment was occurring or progressing through the basin. So this kind of gives you a shot there of the sediment basin. It's about 2,000 cubic feet in storage, about 50 foot long, 25 foot wide at the top. And you can start seeing some of our instrumentation. So these were designed to float at the surface of the basin, and all of our instruments were installed on there. So whenever we were taking a sample, it was at the surface of the basin, of the flow. The way we devised our testing schemes, we had two different test systems we looked at. The first is what we called an empty condition. Essentially, we'd have an empty sediment basin. We'd fill it up with flow and allow it to dewater over 48 hours before we ran a next test. And we would do those tests 3 in a row to simulate a longevity or longevity type of test. Our second type of condition, which I'll only show the second one today, is our overflow condition. We wanted to see what would happen if we had back-to-back storm events, with one storm event overflowing the basin or exceeding the volume capacity of the basin and causing water to flow through the emergency spillway. And those were replicated 3 times back to back to back to, again, learn from those experiments, to learn from the longevity standpoint. We did all of the testing, the phase 1 testing, where we were looking at the coir baffles and our excavated sump and our forebay. That wasn't a whole bunch of exciting, so I'm going to focus on the phase 2, which is where we looked at the lamella settlers. We looked at them in 2 different configurations. We call an upward flow and a parallel flow. And the way lamella settlers work is that the whole idea is that you're reducing the height that a soil particle has to fall out before it gets captured. So I mentioned these are used in wastewater treatment. It also provides laminar flow, hence the name lamella, where there's very low turbulence and it allows those particles to kind of fall out in an ideal setting. So this is what a setup would look like in a wastewater treatment plant in a clarifier. You can see water gets routed in, is forced up the plates, and then treated water comes out the top. So from a schematic standpoint, if you think about a traditional clarifier, a traditional sediment basin, you have an empty tank with a height where a soil particle is forced to fall. That soil particle has flow pushing it out, and it also has gravity acting to weigh it down, to bring it down towards the bottom of the tank. So that particle has to fall out the entire height of that tank. In our sediment basin, we're talking about 3 to 4 feet of impoundment. In a clarifier, it might be 8 to 10 feet. So as you have several particles come in, you slowly start having a layer of sludge built in the bottom, and then you get some particles that end up escaping through the outlet. The lamella system, what it does is it creates a series of inclined plates at about a 55-degree angle. And the way flow is forced through the plates is that it has to come in through the top and then flow through the bottom of the plates before it's discharged out the top. So to kind of blow this up a little bit, If you look at the plates, if you look at just 2 plates, you have a soil particle that's being forced up and out, and then you have gravity still acting, bringing it down. So eventually what ends up happening is that the trajectory of that soil particle takes it to where it hits that subsequent plate or that parallel plate, and it ends up sliding down and being captured at the bottom. So you get a wedge of clarified water going out the top and a wedge of sediment or sludge being caught down at the bottom. So the idea is here that you're taking the entire height of the sediment basin or the clarifier and reducing it down to the distance between the 2 plates, which is 1 to 2 inches. So you're going from 4 feet to 1 to 2 inches. The idea is you can capture more sediment at a faster rate. So that could reduce the amount of time that you have to detain stormwater if you can treat it quicker. Instead of maybe 48 to 72 hours, we're down just a matter of a couple hours. And it might also help us reduce the footprint of these basins. So sediment basins are very expensive to construct because it takes up a lot of right-of-way and a lot of space. Well, if we can optimize the way we use that space, maybe we don't need all of that room. So we went out, we built some lamella plates, and we probably weren't the most efficient and effective at building them the first time. Used a whole bunch of metal to do it. They were pretty expensive, but the idea here is if we can show that they work, we can then worry about trying to make them and try to optimize the design and constructability of the plates. So the way these are installed, they're going into bay number 3 of the basin, so flow would be forced this way. Our skimmer is back here in bay number 4. But once it's all set up and installed, we put in these wing walls to force all the flow to go through the plates. So down at the bottom here, there's an opening where that's the only way water can come in, and then it's forced out the sides. So this is what we call our upward flow, but it's really more of a up and out the side type of flow. With sediment basins, you can't always control the amount of water in there, so you can't get that ideal flow up the top. So this was kind of the compromise we came up with, it's just to come out the sides. This is a time lapse during testing. So water's coming in from the mouth of the sediment basin out here. It's flowing through the bottom of the lamella plates and then out the sides. And from a visual standpoint, you don't see a whole bunch of difference between the two. It still looks like chocolate milk to me between upstream and downstream. This picture, you start seeing a little bit of a difference, and this is after the test has been shut off and you start seeing some of the heavier particles settle out. There's definitely a color difference between the two. Where we really start seeing improvements is when we start looking at our turbidity data. So I mentioned we had turbidity probes in each one of our bays within the basin. So what we looked at was the difference in turbidity between the first bay, the mouth of the basin, and the fourth bay where our skimmer is located, our discharge point. So anything we do in between is a treatment mechanism. So we have 2 plotted lines here. Where your blue line is the standard sediment basin configuration, the red line is a lamella in the upward flow configuration. And what I've done here is I've divided the data for bay 4 by bay 1. And that gives you an idea of treatment efficiency. So anything lower than 1.0 shows you that turbidity in bay 4 is less than turbidity in bay 1. If it's higher than 1, your turbidity is actually higher in bay 4 than it is in bay 1. So this is that turbidity ratio on the y-axis. On your x-axis, you have time. So we looked at the first 12 hours. And where you see these, so that 1.0 kind of divides up the data between higher performing, lower performing. These 2 spikes you see, that's during our inflow period. So I mentioned 30 minutes of inflow. That's where those are occurring. So you actually see the biggest difference between treatment or between turbidity during those inflow periods where flow is being forced through the basin. And then you can see that the lamella system is actually lower than the standard setup. That gives us an indication that it's outperforming the standard setup. We did want to see if we can improve this further. So we took our setup, we removed all of our plates, and we rotated them 90 degrees. So the idea here is that now flow is going parallel to the plates. You still get the advantage where those particles have that trajectory where they're hitting the plates and settling out. But now you're increasing the effective width or the surface area or the cross-sectional area where flow is flowing through. So you're reducing the velocity of that flow as it's going through, and you're getting longer residence time within the tanks. So we put those tanks back in, and we constructed our wing walls, and now we've got that real large opening where water can flow through. So here's that setup. We caulked and sealed all of our open areas along the tanks to make sure we didn't have any short circuiting. We've got this opening at the front where flow is coming through, and the only way out is through the back of the tank. So it has to go through the entire tank system, which is 16 feet long. So there's a good amount of time for that storm water to flow through the tanks. And then our skimmer is located in the fourth bay back here. So we plotted the data again. We wanted to compare it to our two previous tests, our standard setup and then our upward flow setup. So you're seeing the parallel flow here in green, where again that 1.0 breaks down the difference between Bay 4 being higher or Bay 4 being lower than Bay 1. So then we can start making some conclusions where we can take the average data during those time frames and look at trends. So in this case, we kind of clean it up and get a general idea of how things are performing. And you can see again, the parallel flow outperforms the two others. And then we wanted to compare it to our standard. So we said our standard, that blue line, was going to be 1. We'll just call that 1 and divide all of our data by that baseline. So that's kind of what we see here. And that allows us to draw efficiencies. So compared to our standard, the upward flow ranged between 14.5% to about 23% more effective. And then our parallel flow was up to about 32% more effective than the standard flow. We wanted to take it a step further. We realized that having that lamella system was kind of inconvenient, it's expensive, it's difficult to install correctly, and then it would be difficult to move from site to site. It would take a large crane and a large truck to get them moved from different projects. So we wanted to see if we can come up with a different way of doing this and still getting the same benefit. So what we did was we constructed a lamella settling tank that actually goes outside of the basin. So we realized we've got the advantage of using a skimmer. So that's the skimmer that's coming out of the fourth bay of the basin. It's discharging. So this is at the location of the discharge skimmer. And the tank works the same way, where flow is going through the inside here, the inlet. It's going through the bottom and out the top where those plates are installed. And then it's got a weir, a level spreader over here, and a weir where water flows out of. So we're taking turbidity data here, and we're taking turbidity data in the fourth bay to see what kind of treatment we get in between the two. And so here's that data. This is just turbidity on the Y, time on your X. And you can see that the box is installed outside of the basin, that green line. We don't see a huge increase in treatment or in turbidity decrease. What we do see is there's no discharge. So for the first 3 hours of the test, you're actually not discharging any stormwater, which is where you see these large spikes in turbidity. So there's a huge advantage there, where that first flush is kind of being cooled down and condensed in the basin before being discharged. And then this large spike you see here during our second test, our second storm event, that one's being completely canceled out. It's a flat line during that event. So there's benefits there where you get a predictable discharge turbidity rather than having all those fluctuations that you would have during those first flush type of events. So to kind of wrap things up with the sediment basin, I didn't talk about the forebay or the baffle, but we made some changes there that were beneficial. On the lamella settlers, up to 23% treatment improvement. Parallel flow lamella settlers up to 32%. And we also realized that when there's storage, dead storage occupying the basin, you have less resuspension. So there was benefit in having dead storage as well. So this is kind of just a cool drone shot looking at our basin, and just kind of gives you an idea of the way we installed everything there. You can see our emergency spillway, and then that discharge, that skimmer's in here, is discharging this way. So with that, I'll wrap it up and open up the floor for any questions you may have. I do want to thank the Alabama DOT and Auburn for sponsoring the research. And hopefully a lot of these things that I've learned during my graduate studies, I'll be able to transition and do some research here, some exciting research here as well with our state partners. So thank you.
So on each of your experiments on your website, they're documented, you list the specs of geotextiles used. Did you look at different geotextiles? Are they all equal, or you find the woven or non-woven outperform for different applications?
Yeah, so that's a good question. So it all depends on what the DOT prefers as far as materials go. In our case, since we're working with the Alabama DOT, they wanted to see their materials tested. So a lot of the times we're relying on non-woven fabric, which is what they prefer. We did use the non-woven for the Georgia comparison we made with the silt fence sediment barrier.
That was a little of where the question was going.
Yeah.
You know, you're using standards that are already laid out, in which all contractors are going to have to work under that framework unless we convince someone to change the standards. But I was just wondering if you had said, well, we think that maybe if you change the fabric or the material itself or different spec rating, you get higher efficiency. I didn't know if you altered the fabrics themselves.
No, beyond that test we didn't. And I guess what we took away from all these different studies was that it's not a function of the filtration. So it's not how much water can pass through a media, it's how much impoundment you get upstream. That impoundment is what creates the conditions where soil particles start to settle out through gravity. As long as you're not creating a situation where you're going to have failure or flooding, you'd have to manage that as well. But yeah, generally, the larger the impoundment, the more water you can store, and for longer you can store, the more treatment you get.
You have if it really is a function of the impoundment rather than the filtration, then why are we messing with silt fences at all? Why not just put a weir in there?
That's a great question.
We can reuse, like that inlet example, would be very easy just to add a reusable barrel section to the inlet with a weaver on it.
Yep.
It would be a lot better than trying to experiment with all the others.
That's right. I'm not opposed to that idea. I think that's a great idea, yeah.
Did you monitor the compaction of each control that put in, how much compaction it received, or how it was impacted?
Yeah, so every time we install, we would do our proctor test or our in-situ density test, where we take out a core sample and look at our density compared to our proctor, and we were always trying to achieve at least 90% compaction, so we had a good comparison from test to test.
You did test the test, you did it in the same area, was the soil, you brought in all new soil every time? Saturated soil, right?
Yeah, we would muck out the nasty stuff. We'd use skid steers to remove all the heavy material, the loose material. We bring in from our stockpile. We had a stockpile from a certain area, and that was used for all of our tests, so we try to limit the variability from that regard.
Can you go back to your slide where you show the difference between the upward and the parallel? So one of those situations, the parallel, you have coffins on the side, and on the upward you didn't. Did you do any with the upward with coffins?
So you mean
What the difference was between, I mean, how much of an effect did putting coffins on the side have versus parallel and upward?
So we did have walls on the side walls, so that all the flow is going through the system.
For the parallel one you did, but not for the upward one, right?
Oh, we did.
Okay.
Let me see if I can pull it up.
Well, that answers my question.
So that's the upward.
Right.
So you get the side walls on the ends. Is that what you were asking about?
Well, the water can come out of the sides on that scenario.
Oh, yeah, but once it's gone through. So it's got to be forced through the bottom, and then it goes through the tank and out the sides.
Whereas if you oriented the slats the other direction, it wasn't allowed to go out.
Yeah, it's got to go through the entire system. So you get a longer residence time. So yeah, there could be some particles that only come in contact for a few seconds and they come out right at the edge.
Yeah, I'm wondering, how do you account for that impact versus the orientation of the slats?
Yeah, that's true.
You saw your big reduction because of that.
Absolutely,
As opposed
absolutely.
to the orientation of the slats.
Yep, Yeah, that's completely right. And ideally, what you would want is for flow to be coming out the top.
Right.
But you can only do that when you can control the stage in the basin.
Yeah.
And with a sediment basin, being that it's temporary in nature and you can't control rainfall and how much runoff you get, you just kind of have to try to account for all stages within the basin. And that was the best way we could come up with for doing that. But it does make a difference. I agree with you.
We have a question over here too.
Have these been tested like in different regions? Would you expect the results to vary with different soil types and different environmental conditions?
Yeah, that's a great point. So in Alabama, we're dealing with clays and silt that are very difficult to remove. If this had a higher content of sand, I would expect that we would be able to achieve higher effectiveness.
Has anybody ran any of these tests in other regions of the nation?
Not for stormwater. They've been done.
This is kind of a newer testing of trying to make this better.
Yeah, so they've been used in kind of mining wastewater and residential type wastewater. We wanted to see if we can adopt that technology and use it for
So your further
stormwater.
research will be evaluating this under different soil conditions?
Well, what we want to do is, what I want to do is optimize the way these work. So if we can optimize it from a real nasty clay and silt content perspective, we know it'll work great with sand.
Yeah.
And if we add flocculants to the system, which we didn't try here, we could even further enhance it. The idea is if we get it to perform very well without those additional benefits, then it's only just going to improve the performance, right?
The intent here would only be to be operational through the construction period, and then it be just moved out. So you're not looking at long-term maintenance. You're just hoping to be able to optimize it during a construction period, a year or two, and then so on.
Can you repeat the question, that comment?
Yeah, so you're asking about maintenance and how much maintenance may be required during a construction phase, whether it could be just a temporary where you don't have to provide maintenance. And it would depend on, I guess, the duration of the project. These could be built differently where you do have some kind of sediment storage underneath where you can maybe pump out sediment that's been captured. But I guess our idea with this was just kind of see if it worked, provide a means where maybe either a contractor or the DOT would own a set of these and they can be moved around from different projects. Maybe high priority projects would have the tanks installed in their basins. That was the general idea.
I have one sort of confirmation or question that he's talking. So when looking at silt fence installation, looking at silt fence for perimeter controls, for sediment control, not in channels. So based on your results, it appears as though trenching and slicing is less effective than using the, what do you call them, sod, and wrapping the fabric above the surface and using sod.
The sod pins?
Sod pins?
So the slicing didn't perform very well at all, and it was just a function of water flowing underneath and undercutting. So we saw the trenching outperformed slicing. We didn't test the pinning compared to the slicing. It was a side-by-side. We didn't do it for the same sediment barrier. We only did the pinning for concentrated flow areas.
Because I think in Iowa, most silt fence is installed, correct me if I'm wrong, but most silt fence is installed using the slicing.
And we were surprised to see that because with slicing you disturb less ground. You don't have that trench where you could have the susceptibility of undercutting and failure. So that was something we were not expecting. Yeah. Yeah, so I did show some costs, but it was for inlet protection installations. We were just comparing the material costs at that point. We weren't looking at installation labor and costs there. It's difficult for us to compare that because we've got undergrads instead of tractors and got a different labor force. A lot of times we're doing things twice.
There's a lot of proprietary, devices that you guys have any plans to you guys test those as well?
Yeah, that's a good question. When it comes to proprietary products, the DOT didn't want to pay to test those products. They wanted to see how the standard practices performed and create kind of a baseline of what those standards can do. That way when a product comes in and they want to be put on a QPL, qualified product list, they can be compared to the standard practices. And that way the DOT can use the data and they have an understanding of it because they know what their standard silt fence compares to. That's the way the DOT has kind of set it up now, where any product coming in would first be tested at the facility. The facility would generate a report based on the data collected and turn that into the DOT. Then the DOT would make a decision based on whatever limits they they establish.
So it would be nice, Mike starting his career at Iowa State doing research, for there to be funding provided to him so that he could test those products for us in Iowa, and we could make advancements in Iowa. So you guys have any questions? That would be very nice. And Mike, you have, with IDOT or IDOT, did you receive any funding at all to look at any research for them on any products or practices?
So we've got a project that's going to kick off during the summer with the Iowa DOT. We're going to be looking at some of the different practices installed on active construction sites and monitor them during natural rainfall events to kind of see how they perform. So it won't be in a controlled laboratory, but it'll be out in the field and can hopefully get some similar information from a performance standpoint.
So we'll
Well,
definitely
stay
ask him
tuned.
to come back
Yeah.
and share that information with us. So, okay, it's time to break. So you have a break, and then we'll return. Don't forget to vote for the photo contest, and let's thank Mike again.